Good afternoon, professors. This is batch 78. Our project is detection and classification of plant diseases using deep learning. Here, we are using deep learning dense neural network model to classify plant leaves. In our model, we are using four different plants such as wheat, cotton, black pepper, and rice. So, by using this, we will classify whether which disease a leaf has or otherwise if they are healthy. So, this is our first module. Let me run this again. So here we are importing the modules TensorFlow, Keras, and then Matplotlib for plotting graphs and displaying plant image for visualization, NumPy, Mat, and here we are mounting Google Colab Drive because we have to simplify this process. We have uploaded our dataset images to to Google Drive so we don't have to upload over and over again. We are using Google Colab because um, using in deep learning using GPU is a very intensive process. That is, if we don't have GPU, then we have to rely on CPU, and here it can be very time consuming and resource also. But our laptop, we are using laptop here actually. That's why we are not able to use this on our own hardware. That's why we are using this on Google Colab to run this program on Google Compute Engine. You can see here that for Google Compute Engine, they are having 12 GB RAM and 100 GB hardware space, whereas this laptop is only having 8 GB RAM. And then in comparison to Google Compute, we are only having inferior CPU and only integrated graphics card. So as you can see here, we are having 400 different image files. They are belonging to 10 different classes. Some of the classes are cotton. So they have aphid disease, blight disease. This one is cotton hilly. This is mildew disease, and this is belonging to paper class. It has paper blight, paper hilly, etc. And this is for visualization. Here using Matplotlib, we have uh, created a graph of our image dataset for easy visualization. I haven't run this course this time, so I will run this again. And because we have randomized this data set, this time it will give us different batches of image. Okay, as you can see here, these images are different from the ones that was here previously. It is having rice, cotton, pepper, etc. And it is randomized. Here we are allocating our image dataset. So here we uploaded 400 images, and then now we are splitting them into 80% for training dataset and 0.1% or 10% for validation dataset, and the remaining will be again 10% which will be given for testing dataset. So total we are having 16 image batches, and from 16 image batches 80% of it is somewhere around 12.5%, but we are rounding off, so it is 13 batches we are allocating to training images, and two batches we are allocating for validation because 10% is actually 1.8 or something, so we are rounding up again. And here also, because the remaining we directly allocated here without doing any math, that's why it is 1. It is not rounded up. If it was rounded up, then we would have 13 to 2, which would be 17, but we are not having 17 image batches. And this mat.ceil is our rounding function. And here we are shuffling this training, validation, and testing data set. And here what we are doing is resizing the image and rescaling the image, because right now the images are in different size, different dimensions, so we are making them uniform. Also, what we are doing here is data augmentation. We are augmenting the data by doing random flipping and rotation. We are rotating it by 0.2 every time new batch is run after one epoch. So even though we have only 400 images, the computer will treat that 400 images as a different image every time we complete the same epoch. And by the way, we are having 50 epochs, so although for training we are using 13 batches, those batches will be considered different because of this data augmentation. Every time one epoch is completed, so say roughly 500 into 400, that will be considered as the true total image size by the computer, but not for us. So this is our input shape. Here we are having batch image size, and channels. As shown above, we are having three channels because our pictures we need color for our plant disease detection. Although other people will make it one channel, which is grayscale, to save on computation time and memory, but uh, to detect the plant disease, we need to check the discoloration of the leaf. So the leaf is brown or um, brown or dark colored instead of green color, which is why we have included the channel as 3 because we need the color. And here in classes we are having total 10 in classes. Here we are building the model. So first sequential and resize models are there, then data augmentation model, and here we are doing convolution, max pooling until image size is 14x14. Uh, Let me show you down here in model summary. Here initially we are having 256 image size because that is what we made them by resizing above. But by doing convolution and max pooling, the image size is becoming smaller and smaller to improve our computation time, and we are stopping until our image is 14x4. Although this will negatively impact our accuracy, it will help for our computation speed, but later, if we want more accuracy, we can remove this last max boolean and also maybe last convolution function to increase the image size at the cost of slower computation. So by doing this, we will actually improve the accuracy if necessary. And then lastly, we are having flatten because convolution will stack different images. So the 2D images will become 3D, and flatten will reconvert that into 2D. And here we have built a model, that's why we are able to give the summary. Now we are compiling this model. Here we are using Adam optimizer. Here Adam optimizer will dynamically shift the learning rate of the function of the model, so it will save time, because if you have too little learning rate, it will take too much time to learn. But if you have too big number value of a learning rate, then uh, it will not be able to learn accurately. Here we are using only accuracy for our metric because Keras will carry out the model training in batch by batch. So this is not suitable because in small batches the F1 score metrics such as precision or recall does not make much sense. So it has been removed from Keras from version 2 onwards, and we are using version 3.2 something. And for validation, we are using loss, sparse categorical entropy loss function. And here now we are fitting our model. Fitting our model means training the model. So as you can see here, we have 50 epoch. We are using train data set, and we are also using validation data set here. So our batch size is 16, and then sorry, 13, because we are only having 10 data set and we are having 50 epoch. So here this is it is being trained for the first epoch. For the first epoch here we have currently reached 9 out of 13 epochs. So after completing 13 epoch it will test the validation loss, and then it will move on to the second epoch, as you can see down here. So right now here, because we are only starting out, we have an accuracy of 11% for the training data set, and with validation data set we are only getting 10% accuracy. But this will improve, and we are getting 2.3 loss value. This will improve as we keep training our data set model. So our first epoch is completed. Now it will move on to the second epoch. Okay, we have moved on to the second epoch. So now it is training the first batch of second epoch, now second batch of second epoch, third batch of second epoch. Let me fast forward this training so we can continue with our presentation. No problem. Actually, pass. Okay, now I have fast forwarded here, but the power is gone out, so we are not able to complete this stage of the program. But as you can see, previously we continued our training, and whereas we had only 10% accuracy, now we are having 88% to 91% accuracy. So, because there is no power, I'm also not able to run these cells. So these are output from previous time I have run this cell. So here, until now, we have only done for training data set and validation data set. Here we are running testing data set. So from the testing data set, we are getting 92% accuracy. Here we are outputting our graph for training and validation accuracy and training and validation loss. So as you can see here, from 0th epoch to 50th epoch, we are showing our training and testing validation accuracy and loss. And this cell is a model method for predicting confidence. So confidence is basically multiplying 100 with the accuracy, total accuracy. So by doing that, we are running the predict method here, and running this cell, we are out visualizing the output by using matplotlib to show the output image and their confidence level. So here you can see this is the plant blight disease leaf, and the accurate confidence is 99%. Your confidence is 100%, and the actual class is paper blight, and the predicted class is also paper blight. So our confidence level is high. There is there is only one exception, which is in cotton aphid. It has incorrectly predicted as cotton hilly. Thus, our confidence level is only 50%. If we continue training our model, then this error will also be reduced. Here, although the confidence is 76%, it is still predicting correctly. And here we can save our model, so we can prevent having to start from the very first. And here, and actually we are previously we were saving as H5 model, but that format is outdated. So now we are saving it as .keras model. Here, if you want to load our model, we can load here, and I am doing the summary to check the whether the model is correct or not. And here we can do the testing for the loaded model. Accuracy is 88% for this loaded model, which has been loaded after saving it. Okay, so this is the complete presentation of batch 78 project, plant disease detection and classification using deep learning. Thank you.